Okay, we are skipping to chapter 5 because I'm assuming that you've learned everything from chapters 3 and 4 in your previous classes. If you do need assistance with that, please check your folders to make sure that you can do the reviews correctly. Chapter 5 is starting about chemical quantities in the mole, so we're going to do things like solving more mass, balancing chemical equations, doing stoichiometry, things that should be a review but are actually still important enough to go over now to make sure that we're all on the same page. Just like we did with the conversion factors with 12 inches equals to 1 foot, where we have equalities, we can look at counting items like 6 cans in a 6-pack or 24 cans in a case of Coke. A dozen eggs is 12 eggs. Things along those lines. We can think of Avogadro's number as we're counting atoms, molecules, and ions. They actually also left out formula units, which is ionic compounds, if you'd forgotten what those are. And Avogadro's number applies to all of these things, which is why this number could actually become kind of confusing. Notice it's 6.02 times 10 to the 23, and it says items here. That means that it could be 6.02 times 10 to the 23 atoms, 6.02 times 10 to the 23 molecules. The word items changes to one of these 4 options. You'll never have anything besides these 4 options, but all 4 of these options are there. So you really have to understand what you're referring to when you're using this number. And that is, once again, equal to a mole. And that is actually the definition of a mole, is 6.02 times 10 to the 23rd. And that's called Avogadro's number. And don't forget, times 10 can be put into your calculator by using EE or EXP. So you'd be 6.02 EE 23 or 6.02 EXP 23. Notice the really long number here. That's why we need to use the exponents. That will not fit in anyone's calculator. The entire periodic table can be related by this one unit. For instance, 1 mole of any element whatsoever is 6.02 times 10 to the 23. Carbon, 6.02 10 to the 23. Sodium, 6.02 times 10 to the 23. It doesn't matter what element it is, it's still going to have that many atoms in 1 mole. It kind of puts everything on the same playing ground. But let's take this a step further. Aluminum by itself is an atom. That's why it has atoms here. However, if we look at water, water is several atoms bonded together. Which is actually a molecule. So instead of saying we have 6.02 times 10 to the 23rd atoms, we have 6.02 times 10 to the 23 molecules of water. Same with here. Vitamin C is C6H8O6. Instead of using the word atoms, we're using the word molecules because you have several different atoms combined into one thing. Sodium chloride, some people mistakenly call it a molecule, but in reality it's a formula unit because it's an ionic compound. How do you know it's an ionic compound? Well, because it has a cation and an anion. A really easy way to check is you notice that Na is a metal. It's in row 1, which means it's a +1. Cl is in halogen, which makes it a -1. +1 and a -1, you have opposite charges there. Whenever you have the opposite charges, you're going to have formula units. If you look at C, H, and O, if you look at their rows, those are all nonmetals. So that means that those electrons are being shared rather than given and taken. There are no actual charges on those. Okay, so we can actually use Avogadro's number here. Once again, notice the generic term. That means it could be molecules, it could be atoms, it could be ions, or it could be formula units. This is actually used as a conversion factor. Something equal to something else turns into a conversion factor by making it into a fraction. And we talked a lot about that in Chapter 1. If you're confused by that, please go back to Chapter 1 to the dimensional analysis part and review that. So the first thing we're going to do when we're looking at the problem, how many CO2 molecules, so we're looking for molecules here, which if we look at CO2, that makes sense because we have more than one atom bound together. So we're looking for molecules of this in 0.5 moles. Alright, so when we're looking at this, because our representative particle is a molecule, we don't have to figure out how many atoms or anything like that. This is actually a fairly easy one. Put our number over 1. First thing you want to do is figure out our conversion factor. Because we're going from moles to molecules, we need 1 mole is equal to 6.02 times 10 to the 23rd molecules. Put our number over 1, just like we did with our conversions. We have moles on top, that means we want to put moles on the bottom. If we look at our conversion factor, we notice 1 goes with moles. That is equal to 6.02. So it could be moles cancel out. 0.5 times 6.02 times 10 to the 23rd. Remember to put times 10 to the 23rd, you're going to put EE or EXP. Do not put times 10. That should come out to be 3.0 times 10 to the 23 molecules. If you did not get that, and you're pretty sure you have it set up right, I would make sure that you're putting in this part correctly, because that's where most people make their mistake. Alright, let's try another example. We have 2 moles of aluminum. Notice aluminum is a single element with nothing bonded to it. That's why it has atoms here rather than molecules now. So first thing we want to do, we want to know how many atoms are in this many moles. So that means we need the Avogadro's number again. 6.02 times 10 to the 23 atoms this time rather than molecules, because of the fact that it's a single atom, is equal to 1 mole. Next thing we want to do is we want to put what we're trying to convert over 1. We have moles on top, that means we want to put moles on the bottom. If we look at what our conversion factor says, it says 1 goes with moles. 6.02 goes on the top then. Moles cancel. 2 times 6.02 times 10 to the 23. That comes out to be 1.2 times 10 to the 24 atoms. Alright, let's try one more. Once again, how many moles, so they're asking for moles of sulfur, no single sulfur, that's not bonded to anything, which means we have it in atoms. So, because we're going from atoms to moles, we want to figure out the Avogadro's number. We have atoms on top. That means we want to put atoms on the bottom. If you look on our chart, atoms goes with 6.02. That is equal to 1 mole. Atoms cancel. That means 1.8 times 10 to the 24th divided by 6.02 times 10 to the 23. That comes out to be 2.99. However, we only want two significant figures. So that becomes 3.0 moles of sulfur. Now, if you got this one wrong, it is very likely that you're putting the times 10 in wrong. So either check your manual or go see somebody to make sure that you're putting it into your calculator correctly. Now, if we look at moles to examine molecules and relate them within a single molecule, we can. For instance, if we take 1 molecule of aspirin, we have 9 carbons, 8 hydrogens, and 4 oxygens. That's how many carbon atoms we have for 1 molecule. Now, nobody ever actually takes 1 molecule of aspirin. You actually want to take a larger quantity. Well, in order to be able to decide how much we need, we usually end up having it in grams. Well, in order to get it into grams, we need to put it into moles. So, this 9, and this 8, and this 4 can actually translate directly to moles. So, there are 9 moles of carbon, there's 8 moles of hydrogen, and 4 moles of oxygen in every complete mole of aspirin. Just like there's 9 atoms, 8 atoms, and 4 atoms in a molecule. In a whole mole, there's 9 moles, 8 moles, and 4 moles. You see how this relates here. For every 1 molecule, 9 atoms of carbon, same thing as 9 moles if we're referring to a whole mole of the compound. We basically multiplied this whole thing by Avogadro's number, and it would actually come out to be equivalent. Which means we could actually then use those numbers in the subscripts themselves in the molecule as part of a conversion factor. For instance, for every 1 mole of aspirin, we need 9 moles of carbon. For every 1 mole of aspirin, we need 4 moles of oxygen. So let's take a closer look at this. We have 0.15 moles of aspirin. We want to know how many oxygen atoms there are. Notice this is a molecule because of the fact that they have several different atoms bonded together. Yet it asks specifically about oxygen. So, we have 1.15 moles of aspirin. So for every 1 mole of aspirin, we have 4 moles of oxygen. And I got that from the subscript. And I'm going to replace the word aspirin with C9H8O4 just to reiterate that. Once we get it in moles, then we can get from moles to atoms, because 1 mole of oxygen is equal to 6.02 times 10 to the 23 atoms. Alright, so we're going to put the number we're trying to convert over 1. Okay, so for every 1 mole, notice that we have the C9H8O4 on the top. That means I want to put that on the bottom. For every 1 mole of aspirin, we have 4 moles of oxygen. Okay, we've used that now. We don't need to use it again. For every, we have moles of oxygen on the top. That means we want moles of oxygen on the bottom. And here's our other conversion factor. There's moles of oxygen. 1 goes with moles. 6.02 times 10 to the 23rd goes on top. So it'd be 0.15 times 4 times 6.02 times 10 to the 23rd, and that comes out to be 3.6 times 3.61 times 10 to the 23rd atoms of oxygen.